Okay, good afternoon and good morning, everybody. We're going to be going over the test review, questions 7 through 10. And whenever you do these, you need to have, whether it's on the test or practice at home, first off, you need to have, of course, you got to have your question sheet, in this case, the review sheet. You need to have your roadmap of the mole. Make sure you have this ready to go to help you. And a periodic table, because you're probably at some point going to be asked to figure out molar masses. So we're starting here with number 7. We zoom in. So question number 7, it's asking how many molecules of NO2 are produced from this number of molecules of N2O4. We've got the balanced equation here. We have a mole ratio of 1 N2O4 for 2 N2Os. And let's see, let's work out what's given on this problem. How many molecules of NO2? So we're looking for molecules. Since this is what we're looking for, I'm just going to put it on the right side of my equation. So I'm going to call this one NO2. And we're looking for number of molecules. So I'm going to end up over here with an answer, blank molecules. And in this problem, let's see what's given in number 7. It tells us when we have 3.5 times 10 to the 22 molecules of N2O4. So on this problem over here, I'm going to say that molecules A are N2O4. And we're starting with, this one right there, 3.5 times 10 to the 22 molecules. 3.5 times 10 to the 22 molecules, 22 molecules. And that's of N2O4. Can you see that on the screen okay? Yeah. So in this problem, we're starting here. We're going to convert to moles. We're going to use our mole ratio of moles of NO2 over moles of N2O4 to give us moles of NO2. And then we're going to convert it back into molecules, a 3-step conversion. So let's get to work here. Number 7, we're given 3.5 times 10 to the 22 molecules of N2O4. That's what we're given. Am I okay so far? I haven't made a mistake? And since we're right here, we need to turn it into moles by multiplying by mole over Avogadro's number. So let's see, 6.02 times 10 to the 23 molecules. Molecules of N2. Now look I know this gets kind of a pain because you got to write all this stuff, but if you want to get the question right, this is what you'll do. In 1 mole of N2O4. So at this point, molecules of N2O4 cancel and we end up with moles. We're right up here. Now we need to set up the molar ratio. So we need to go moles of NO2. Let me get rid of that, was from a previous problem. Moles of NO2. How many moles of NO2 do we have in the balanced equation? Come on, everybody, take a look. How many moles of NO2?
2.
We have 2 moles. 2 moles of NO2. Whatever we're trying to convert to, that'll be on the top. And how many moles of N2O4 do we have?
1.
1 mole of N2O4. So at this point now we can cancel out dinitrogen oxide and we're left with moles of NO2, but that's not what we're looking for. We need to get to molecules of NO2. That's the question was asking. And to get to molecules from moles, we will multiply by Avogadro's number. So 1 mole of NO2 is 6.02 times 10 to the 23 molecules of NO2. Molecules of NO2 cancel, moles of NO2 cancel out. And now we can start crossing off numbers. We'll use lucky green to do this part. First off, let's get rid of this big, huge number. Avogadro's number will cancel like that. So are we now down to everything's this is 1, and that becomes just 1. So now we got 1 times 1 times 1. Okay, what's 3.5 times 2? Because that's what our answer is going to be. What is 3.5 times 2? I'm going to put it here. 3.5 times 2. We got 3. Actually, it's 3.5 times 10 to the 22 times 2 equals 7 times 10 to what? To the 22. And again, we were looking for molecules of NO2. Question there? Yes?
Well, I was going to say, do you have to leave it the 7 times 10 to the 22nd, or do you have to convert it to
You know what? Okay, so you're asking, do we need to convert this into scientific notation? At this point, since it's just one number, it is scientific. Actually, true scientific notation for that would be 7.0 times 10 to the 22. Since it's just a single number there, you don't have to convert it to scientific notation because it wasn't big enough. If it ended up that this was 14 times 10 to the 22, then we would have to make it 1.4 and then make it times 10 to the 22. This one, we're okay. Let's work on number 8 right now. Okay, in question number 8, we're given this equation. It's asking how many liters of CO2. So we're looking for liters of CO2. And we're given in this problem 50 grams of calcium carbonate, which is chalk. We did the lab with that before. And then is heated according to, okay, that's extra information. You don't need to worry about it. We just need to have this balanced equation. So in this problem, I'm going to put the given is calcium carbonate. So I'm going to now change this from what my previous problem was, CaCO3. And we're looking to change this into liters of CO2. So now this is going to become CO2 on this side. We're looking for liters up here. So this is where I'm going to end up, looking for liters of CO2. Get rid of all these past problems I worked so they're not distracting me. And in our problem, we're given 50 grams. So we're going to start over here with 50 grams of calcium carbonate. So in this problem, we've got a 3-step conversion. We're going to moles of calcium carbonate, mole-mole ratio to get us to moles of CO2, and then we're going to convert that into liters of CO2. So we start off with what's given, 50 grams of calcium carbonate, and we're going to go to moles, so we're going to do multiply it by moles per gram. We need to know the molar weight. So let's see, what's the molar weight of calcium carbonate? Got 100? Because you were able to get that by looking on your periodic table and seeing that calcium is 40, and then we had carbon is 12, and then we had 3 oxygens. When you add those all up, we get 100 grams of calcium carbonate. Now that'll be a bummer on the test because you're not going to have your reference chart. You'll have to be prepared to add up molar masses. And that'll be 1 mole of CaCO3. Now we got to set up our mole ratio because we've already set this up. We've got it to mole here. So now we need to go moles of CO2 over moles of calcium carbonate. Moles of what we're going to over moles of what we came from. How many moles in the balanced equation of CO2 are there? 1? Just 1 mole? Yep. And if it helps you out, go ahead. If it helps you to put the coefficients in front, do it. There's 1 mole of CO2. And how many moles of calcium carbonate are there in the balanced equation? 1 mole. So this is a 1-1 ratio. CaCO3. Oh, okay, so it canceled the grams. Now we're got rid of moles. So now whatever this number, right now it looks like it's what? 0.5 moles of CO2. 50 divided by 100 is 0.5. Now we need to go to volume, and we get volume by multiplying by the ideal gas law constant, which is 22.4 liters. A lot of these questions are going to say at STP. That's just at standard temperature and pressure. For right now, we don't need to worry about that. That'll be the next unit. 1 mole of CO2 gas takes up 22.4 liters of CO2. Moles of CO2 cancel. Over here, we can reduce 50 and 100 really easily, can't we? What do we reduce it to? 1 over 2. And then 2, oh, I can reduce this just to make it easier. How many times does 2 go into 22.4? It'll go 11.2 times. We're just taking half of that. So what we've got now is we've got 1 times 1 times 1 times 11.2. And in the bottom, we've got 1 times 1 times 1 is 11.2 liters of CO2, our answer. Okay. And lastly, in any chemical reaction, which two quantities are conserved? Mass, whatever mass you start with in the reactants, you're going to have in the products, and number of atoms. The last unit was all about balancing equations. We were just making sure we had the same number of every atom in the reactants as we did in the products. Any questions there? Going once? Going twice?